Let us discuss an important organic reagent, Gilman reagent. Gilman reagent is represented as R2CuLi, R2CuLi, where R is alkyl or aryl or allyl or benzyl. It is named as lithium dialkyl or diaryl cuprate. Lithium dialkyl or diaryl cuprate. It is prepared by treating organic lithium reagent with cuprous halide in presence of either dry ether or tetrahydrofuran, usually at low temperature. For example, lithium dimethyl cuprate is prepared by treating methyl lithium with cuprous iodide in presence of ether. See, Gilman reagents have a less polar carbon metal bond, that is carbon copper bond. It is very less polar compared to other organometallic compounds such as Grignard's reagent, where the metal carbon bond is carbon and magnesium. It is comparatively highly polar because magnesium is more electropositive than copper in Gilman reagent, and hence we can say Gilman reagent is less polar. Gilman reagents have less polar carbon copper bond, and hence it is less reactive compared to other organometallic reagent such as Grignard's reagent or organolithium compound, and hence it is very selective in its reaction. Important reactions of Gilman reagent are substitution or coupling reaction and conjugate addition reaction. These reactions are not given by other organometallic reagents such as Grignard's reagent or organolithium reagent. They do not participate in the substitution reaction, that is similar to SN2 reaction. And conjugate addition usually taking place in alpha beta unsaturated ketone. Okay. One of the important type of reactions given by Gilman reagent is substitution type reaction or coupling reaction. Coupling of Gilman reagent with organochlorides or organobromides or organoiodides is useful in organic synthesis because it forms a carbon-carbon bond, a new carbon-carbon bond. During this type of reaction, during the coupling reaction, one of the alkyl groups from Gilman reagent replaces halogen from the organohalides. It replaces halide from the organohalides. One of the alkyl or aryl group present in Gilman reagent replaces halide from the organohalide to form higher hydrocarbons, usually higher hydrocarbons. This coupling of two alkyl or aryl groups by the formation of carbon-carbon bond is utilized by Corey and Hauser, and the formation of higher hydrocarbons using this coupling reaction is known as Corey-House synthesis. Okay. These type of substitution reactions are not given by Grignard's reagent or organolithium compounds. See, there is no reaction or no substitution reaction with alkyl or aryl halide with Grignard's reagent. Same condition but no reaction with Grignard's reagent. That's it. Okay. Now let us discuss some of the important examples for coupling reaction. For example, lithium dimethyl cuprate Gilman reagent reacts with this alkyl halide. One of the alkyl group from the Gilman reagent attacks this carbon atom, replaces iodide, as in the case of SN2 reaction, forming this hydrocarbon, where a new carbon-carbon bond is formed. You can see methyl group from the parenthesis gets substituted for iodide in this reaction. Similarly, lithium diethyl cuprate reacts with iodobenzene. The ethyl group from the parenthesis attacks the carbon atom of this phenyl group, replaces iodide to form ethyl benzene. Okay. Similarly, in this reaction, chlorocyclopentane reacts with lithium diethyl cuprate, forming ethyl cyclopentane. Here, ethyl groups attacks this carbon atom, replaces chloride, forming ethyl cyclopentane. In the next reaction, 1,1-dibromocyclopropane reacts with the excess of Gilman's reagent. 2-bromide ion gets replaced by the methyl group, forming 1,1-dimethylcyclopropane. Similarly, in the next reaction, here configuration is represented. You can see in this chlorohydrocarbon, chlorine situated in the below the plane of molecule, below the plane, and hence methyl group attacks this carbon atom. Configuration gets inverted, as in the case of SN2 reaction, forming this product. You can see methyl group lie above the plane, whereas chloride, which gets replaced, it is the leaving group lying below the plane of the molecule. Then in this next case, there are two halide ions, chloride and iodide, in this molecule, in which iodide is good leaving group compared to chlorine. That is why when it reacts with lithium dimethyl cuprate, iodide gets replaced instead of chlorine because it is good leaving group, forming chlorobutane. Okay. As we discussed earlier, Gilman's reagent can reacts with vinyl halide also, replacing halide of vinyl halide. Coupling reaction takes place, forming corresponding compound, hydrocarbon. For example, you can see lithium diethyl cuprate reacts with this vinyl halide. You can see the configuration of this vinyl halide is trans in presence of ether at about 0 degree centigrade, forming this olefin or alkene having the same configuration as the vinyl halide. That is, stereochemistry is maintained in the product. See, it is trans vinyl halide. The product is also trans. Stereochemistry is maintained. That is one of the important characteristics of Gilman reagent. In Gilman reagent, stereochemistry is maintained during the reaction. Okay. In this example, you can see it is 1-chloropropene. It is trans 1-chloropropene. When it reacts with the lithium dimethyl cuprate, forms trans butene. Here also stereochemistry is maintained. Trans substrate molecule, product is also trans. Similarly, in this case, it is cis 1,2-chloropropene, which on reacting with the Gilman reagent, lithium dimethyl cuprate, cis product, it is cis butene is formed. When the substrate is trans, the product is trans in the first case. When the substrate is cis, the product is also cis. That means stereochemistry is maintained during the reaction. In this reaction also you can see the stereochemistry is maintained. It is 1,2-diiodoethene, which is trans 1,2-diiodoethene, which on treating with this Gilman reagent iodine gets replaced forming these products. You can see the product having same configuration as the substrate molecule. It is trans, the product also trans. Okay. See, one of the important characteristics of other organometallic reagents such as Grignard's reagent and organolithium compound is their 1,2 addition with the carbonyl group. But Gilman's reagent does not give 1,2 addition with the carbonyl group. It doesn't react with the carbonyl group. See, for example, if you treat this parabromocyclohexanone with this Gilman's reagent, you can see Gilman reagent does not attack this carbonyl group. Instead, it replaces bromine by SN2 reaction, forming the substituted product. Instead of 1,2 addition product, it gives substitution product. Okay. Another important reaction of Gilman's reagent is its reaction with acid chloride. With acid chloride, it gives ketone. Here also, there will be no 1,2 addition reaction, but instead it replaces chlorine or halogen from acid chloride or acid halide, forming corresponding ketone. For example, you can see it is an acid chloride. It reacts with lithium dimethyl cuprate. We get this carbonyl compound, a ketone. The mechanism of such reaction can be represented like this. It is an acid chloride. When it reacts with Gilman reagent, the nucleophile C3 negative attacks this carbon atom. Thereby, this carbon oxygen pi bond shifted to this oxygen atom. Thereby, this anion is formed first. But by the rearrangement, it replaces a chloride ion, forming corresponding ketone. Instead of addition product, we will get the substitution product. Another example is this. It is acid chloride paranitro benzoyl chloride, paranitro-benzoyl chloride, which on treating with lithium dimethyl cuprate, we get corresponding ketone, paranitro-acetophenone. Another important reaction given by Gilman reagent is its reaction with epoxides. With epoxides, it gives corresponding alcohols. For example, this epoxide on treating with lithium dialkyl cuprate, Gilman reagent, the R group attacks comparatively less hindered side, that is here, forming corresponding alcohol. The R group does not attack this carbon atom because there is a methyl group which hinder the attack, so that it will attack the less hindered position, thereby forming this alcohol. That is another important reactions given by Gilman reagent. Okay. One of the important characteristics of Grignard's reagent, is its 1,2 addition with a carbonyl compound. For example, cyclohexanone reacts with methyl magnesium bromide, Grignard's reagent, followed by acid workup. You will get corresponding alcohol. But Gilman's reagent will not react with the carbonyl compound, forming such alcohol. Similarly, one of the important aspects of Gilman reagent is its 1,4 addition, that is what is called conjugate addition. 1,4 addition with alpha beta unsaturated ketone. For example, see Grignard's reagent on treating with this alpha beta unsaturated ketone, it attacks only the carbonyl group to form 1,2 product, 1,2 addition product. Here, the carbon-carbon double bond gets intact. But if you treat the same alpha beta unsaturated ketone with the Gilman reagent, 1,4 addition takes place. 1,4 addition takes place to form methyl substituted cyclohexanol. Here there is no 1,2 addition as in the case of Grignard's reagent. That is one of the important characteristics of Gilman reagent. That is, Gilman reagent gives 1,4 addition with the carbonyl group if it is alpha beta unsaturated compound, but Grignard's reagent and Organo lithium reagent also gives 1,2 addition with the carbonyl group. Okay. Now see the mechanism of this conjugate addition. One of the methyl group of Gilman reagent attacks the beta position of ketone. The carbon-carbon double bond ruptures, forming a resonance stabilized enolate. You can see the enolate formed by this bond shift will be stabilized via resonance. This resonance stabilized enolate in presence of acid workup forming corresponding ketone through 1,4 addition. See, it is 1, 2, 3, 4. It is 1,4 addition. Here methyl group attacks at the beta position, carbon-carbon bond ruptures forming this enolate. This enolate gets resonance stabilized, and in presence of acid workup it ultimately gives the product ketone, methyl substituted ketone. Here it is methyl substituted cyclohexanol. One of the example of alpha beta, the conjugate addition is reaction of alpha beta unsaturated ketone with lithium dibutyl cuprate, the Gilman reagent, in presence of boron trifluoride and ether at minus 78 degrees centigrade. It gives butyl substituted ketone. Here butyl group gets substituted at the beta position of this carbonyl group through the 1,4 addition reaction. This product is formed. Okay. Another important example for this 1,4 addition or conjugate addition is this. It is an alpha beta unsaturated ketone which on treating with lithium dimethyl cuprate followed by acid workup, you will get this ketone. Here methyl group gets substituted at the 4th position, beta position of alpha beta unsaturated, beta position of carbonyl group of alpha beta unsaturated ketone. Similarly, another important example for 1,4 addition or conjugate addition is this. In this case, you can see this molecule. It is also an alpha beta unsaturated ketone where there are 2 double bonds inside the ring, which on treating with lithium dimethyl cuprate in presence of tetrahydrofuran below minus 78 degrees centigrade, at minus 78 degrees centigrade followed by acid workup, you will get this product. Here there are 2 carbon-carbon double bond, and hence this position also is alpha beta unsaturated carbon atom, and this position is also alpha beta unsaturated carbon atoms, and hence methyl group may attack this position or this position. But you can see methyl group doesn't attack this position because sterically it is sterically crowded. The ring junction is sterically crowded, so that the methyl group attacks at a comparatively sterically less hindered position, and so here the methyl group attacks forming this product. Okay, here this methyl group is in the thick wedge, that is methyl group above the plane, and hence the new methyl group gets or it lie below the plane, so that this configuration. Another important example for 1,4 addition is this. You can see this hydrocarbon part within the parenthesis attacks this position, beta position of carbonyl group, alpha beta unsaturated ketone, and you will get this product. Okay, here also 1,4 addition takes place, conjugate addition. Another important reaction can be represented like this. Here also 1,4 conjugate addition takes place, and hence methyl group attacks at this position, beta position of carbon-carbon double bond. You know the carbonyl group at the beta position. Thereby methyl substituted ketone is formed through 1,4 addition. Okay, that is another important example. You can see here the product is more favorable, trans product. Here this methyl group and this methyl group lie in trans positions, and it is the more favorable product or major product of this addition, 1,4 addition reaction. Methyl group trans to this methyl group. This methyl group is trans to this methyl group. That is the case. Okay. This is another example of conjugate addition given by Gilman's reagent. It is an alpha beta unsaturated cyclic ketone which reacts with this unsymmetrical Gilman reagent. You can see here is a vinyl group and it is a methyl group in the first step, followed by in the second step the product reacts again with this allyl bromide. What would be the final product? See, in this reaction, first of all, 1,4 conjugate addition taking place, where this, you can see here is a methyl group and here is a vinyl group. See, vinyl group is more nucleophilic than methyl group, and hence vinyl attack takes place in this beta position to form this enolate anion. This enolate anion reacts in the second step with this allyl bromide. You can see this bond shift, thereby this carbon attacks to this carbon, forming the required product by the ejection or by the replacement of a bromide ion. Thereby this product is formed as the final product. Okay. Yes, it is all about Gilman's reagent. Thank you for your listening. Okay.